This video is by no means the correct way to do everything in LabVIEW for FRC, but it's just a compiled repository of all of the different things that I've learned while on the team, and I feel like this is important to give on to the next generation of teams, that way none of the ideas that I have had are lost. Some helpful resources for any FRC programming that you do, or electrical problems, or just problems in general, is going to be Chief.fi. It's basically just Reddit for FRC. You can see a whole bunch of different threads. You can check out them, you can search them, use that for any questions that you can't solve or any issues you run into. Another one, more for the LabVIEW side and coding side, is going to be WPI lib. This one is more for like the software and like updating your RoboRio and all of the other stuff. It's more specialized towards software and electrical. So to start out with, I am going to show how to create a RoboRio project. So after you get LabVIEW installed for FRC, you'll want to make sure everything's all set up. There should be guides to do that on WPI lib, and if you can't figure that out, you can check Chief.fi and get that. And once you get all that done, you will go to FRC RoboRio project. You can name it whatever the heck you want. So let's just do video. You want to put in your team number. So my team number is 2848. You want to figure out where you want to save it. That's fine for now. And then you don't mess with anything else. Everything else you just leave. Alright. So this is your main panel for any LabVIEW coding you're going to be doing. There's really only a couple areas you need to access. So team code is going to have all of your VIs that are important, and that really this is where you're going to do most of your programming, pretty much really all of it. And then the other one is build specifications. This is for deploying the code to the robot, and we will go over that a bit. So first thing I want to do here is just kind of do a little run through with a brief explanation for what each of the VIs do. Autonomous independent is going to be obviously your autonomous mode. All of your autonomous code is going to be in here. Begin.vi, this is where you initialize and declare all of your motors, your sensors, everything you have in your robot. Disabled, I never really used that, don't need to worry about it. Finish.vi, this is where you terminate or close all of your motors and sensors just to make sure everything it will be properly reset for the next time you start up your robot. Periodic tasks are for obviously timed tasks, and these are ones that are going to be running in a loop. So any loops you're going to be having, you want to put them in the periodic tasks VI. Robot global data, this is for global variables. This is for sharing information in between VIs. So like if you are getting information in teleop and you want to share it to your periodic tasks, you have to create a global variable and use it through that in the robot global data VI. Test VI, I never use this. This is for, like it says, testing your robot. And this can be used to run like checks in between matches where you test each of your subsystems. I never had the time to do this just because I was the only programmer, but if you feel like messing around with that, go ahead. Vision processing, don't even know what that does. I never touched it, don't worry about it. And then robot main, you're pretty much never going to edit robot main. You want to be really careful not to delete any of these accidentally, because that will mess up your whole program and you have to basically make a new one in order to get it working again. The only thing you're ever going to add into robot main is if you're using a NavX IMU sensor, you're going to need to add in a couple of blocks of code for that in here, but that's it. Alright, let's see. So let's start in the Begin VI. And you'll see that out of the box you have a whole bunch of stuff that means absolutely nothing to you right now. So the thing with LabVIEW is instead of having text and variable names, and it does have that, but instead of being a text-based code, it's a block-based code. And to connect these blocks you have your different wires. And the different colors of the wire mean different things. So green is a boolean, so it's either true or false. Blue is an integer, so this is like a 0, 1, 2, 3, 4, 5, and so on. Orange is going to be your doubles, so that's your decimals. Purple is any of your strings. It's like left and right motors is the reference name for the drive motor here. This brown one right here is a cluster. So if you take an unbundle and you unbundle the cluster, you can, this one only has one, I think. Let's see here. Get a cluster, let's do unbundle by name. Yeah, so this one only has a device integer in its cluster, but sometimes they will have a whole bunch of different types of variables and constants and whatnot inside of the cluster that you can pass through. So pretty much a cluster is just an array of multiple different types, while an array is usually just like an array of strings or an array of integers. It's not an array of integers and strings. To start your most basic begin, really you don't need any of this. All you need to make sure you don't delete is the section I've highlighted. This has to do with like the main functionality of the VI, and if you delete that, it's a pain in the butt to fix, just like how you don't want to delete anything in the main VI, but everything else you can delete. Now what we're going to do is we are going to set up a basic tank drive base code. So what we're going to do, let's say we are using, and also once you get all LabVIEW stuff installed, you'll have all of these libraries available to you. Let's say we're just using 2 SparkMaxes. Let's go ahead and name device numbers are going to be your CAN IDs. So let's do like 10, 11. These will be set from the SparkMax controller. I think it's called the Rev Hardware Client. And in there you will set your IDs and make sure you have them on whatever you need. Alright. So let's do registry set. This is going to create the reference names for these 2 motors. And if you just highlight something, press Control U, you can organize it. So let's have 10 be left drive, and let's have 11 be right drive. If you need to configure any extra sensors, you can always do that in here as well, but for now it's just going to be simple. We can just leave it like this. Alright, so this is all of our initialization and declaration of our 2 SparkMax or Neo motors, whatever you want to call it. So now we are done begin. So you can press Control E and then Control W to switch to the main and close it. So now let's go to Finish. Make sure we properly terminate our motors. You can delete all the comments and you can delete these too, but you want to leave everything else. And Control B will get rid of all the broken wires. You see as X, so you press Control B, deletes them all. Alright. Now let's go back to our Rev Robotics. Let's do registry get. So you're going to be getting those 2 motors information, and then you'll do the close, put it inside of the bracket, so that way. Then you're going to connect the wires, create your constants. Oh, that's not what I wanted. Let's do left drive, and then we'll do right drive. And then this yellow line here is your error. So this is useful for debugging, where whenever you have VIs with the yellow error out and error in connections is made, if the first VI has an error, it won't run the second VI that's downstream and cause another error. It'll just produce one error at the VI that failed, so that way it's easier to tell what went wrong. Because you know it won't run here at the motor get and not at the RevMax close. And the purple one is just our control device reference, and that is just pretty much this is the motor we are closing, and this is the other motor we're closing. Alright, so now our finish and begin are both completed. And going back to begin, let's say we had more than one motor on each side of our drive base. What do we do then? Do we want to have 3 different motors all named different things that we have to access? Or do we want to just have it under one motor that controls everything, just so that we have left drive only and right drive only? We don't have like left 1, left 2, and left 3 drive. So what you do for that is you go to your configuration in your RevMax tab, and you'll get the follow BI. And what this will do is it will create a follower leader system with the motors. So you will have one motor be the leader, and the other 2 will just follow. So what we're going to do, let's see here, master controller. So let's have this one here be master controller, and then these 2, we'll change those to the correct CAN IDs, which are for now are just arbitrary. And then we will add them to the motor control device ref, so that is the motor we are addressing, and this is the motor that they will follow. And now you want to make sure when you're going to do your registry set that you go to the master controller, and you don't go to the other motors. So if you do that, it will only activate that one motor, and it won't activate the other 2, because that you're just addressing a follower and not the master or the leader. But if you address the leader, the other 2 will do the same action as the master motor. And now we'll just do the same thing for our other side. You just copy paste it, pretty easy. Change that and change it to your different CAN IDs. So for this one, let's see here. It looks like we have 16 as the master, and this one we have 11 as the master. So let's go ahead and make it nice and patterny, nice and simple, where the lowest number in each side is the master. And right now, your Finish.vi does not need to change, because you're still getting the master motors, and you're closing those master motors, and that also closes the follower motors with them. At least that's what I've seen in my code. I don't need to make 4 more closes for the other 4 motors that are the followers. I can just do the 2 masters and it's fine. Alright, now that we have all our motors initialized and set up, and they're all going to close correctly, and we're not going to burn anything down, we're going to go into teleop. And we're going to start getting input from our joystick and applying it to these motors that we have created. So let's get rid of all this rubbish, don't need that. Get rid of the comments here. And once again, do not get rid of these couple of things. These are integral to the main functionalities and basic functionalities of the teleop VI, and also like the main VI. So don't delete those. And then, let's see here. What we're going to do is we're going to get input from a joystick. Oh, wait. But we can't just all of a sudden say, okay, get the joystick reference and then get values, because we have not declared our joystick yet. So what we have to do is go back to begin, do a joystick open and a joystick set, and joystick device, so it's USB 0, that's fine. Just name it the default name, I don't care right now. And that's it. And now you want to make sure you do the matching code in Finish.vi, just to make sure everything works all nice and tidy. See, this one has no error, so you just can't wire it, and that's fine. Alright, now we go back to teleop, get our name. Let's see, scalar, POVs. Okay, so for the joystick, you're going to have a couple different options for controlling it. You got your axes, which is obviously just your joysticks. You got select your buttons, which is like your shoulder buttons, your A, B, X, Y, or triangle, square, whatever you're using. And also, like if you push down the joysticks, and then your D-pad is going to be in your POVs. That one is used less often. But what you're going to have to do in order to get at these values is you're going to have to do an index array, because these are all arrays of these values. So this is an array of all the axes values. This is an array of all the button values. This is an array. Actually, I don't think this is an array. The POVs function slightly differently. You can check online for how that works, but I'm not going to go into that one. So for now, we're just going to grab our axes, and we are going to want to pick a specific axis. So go to your Xbox Axes Indexer, and then pick your axes. So let's do left Y, right X, and right Y. Let's get all that wired up to our inputs. So this will function like any normal array, where it starts with 0 and goes on, but these different selectors have the preset values or preset integers for that axis. So right Y just gives it the index for right Y, and that's what the output you get on the other end is. And usually for VIs, left side's input, right side's output. Alright, so now we have all of our inputs for the axes, and we're getting all of our outputs out. And we're going to want to use these outputs to drive the motors. So what we got to do, let's do registry get. We got to get the pretty much the names or the device reference for all of our motors so that we can actually use them. So left drive and right drive. Alright. And here's where you have to start kind of using your brain a little bit, because the rest of this is pretty much just automatic and just setting up, and you just do this every single time. But here you need to decide how you want to control your robot. There's a couple different ways. There's tank drive, which has your left side, so your left Y and your right Y. Left Y controls left motors, and right Y controls the right motors. Or you could do arcade drive, which just uses left Y and left X to control both sides of the drive base. So I'm going to do both of those just to show how they work. So let's just do tank. Tank drive is the simplest version to set up because it's really simple. You just take your left Y, you take your right Y, and you just plug them in. And boom, you're done. You have a driving robot. As long as everything's wired up correctly and you don't have any other underlying issues, that is going to be all of the code you need for tank drive. And this is a very simplistic drive style that if you have tons of practice on it, it can be very useful. But if you don't, it can be a little bit unnatural. But since a lot of people have grown up playing games, one thing that may be more natural for them is arcade drive. Arcade drive is a bit harder to set up. So for arcade drive, let's get our set outputs. We're going to have a couple of conditions for how your robot drives. So here, for these conditions, we're going to use comparisons. And we're going to be determining what the state is of our joystick. And remember, for arcade drive, we're just using the left joystick. So we have a couple different conditions for arcade drive, or a couple different ways that it can drive. So it can do forwards, backwards, and it can turn. And that's simple arcade drive, that's just what we're going to do. So for forwards, backwards, we want to determine, really we want to set when it's forwards and when it's turning. So we need to set limits on what certain values need to be in order for it to be considered going straight or turning. Okay, so before we go into arcade drive, I'm just going to show a pretty quick dead zone example because out of the box your controllers may be a little bit too sensitive right near 0, and so you can just create a dead zone. All of your outputs from your axes are from -1 to 1, so 0.1 will be about a 10% dead zone where you're just applying that. So if it is less than, case structure is just an if, so we're saying we will grab the value of this axis, find the absolute value, just so we don't have to deal with negatives and positives, and then if it's less than 0.1 we do x, if it's not we do y. So if it is less than 0.1 we are going to just take our output and just make it 0. And then if it is not, we're just going to take our input and make it our output. And you want to grab it from before the absolute value, so you're not grabbing the absolute value of the input. And now that is how you do a dead zone. And you can just copy paste this to the other 4 axes to get your dead zone applied to all of them. And once you've learned a bit more about how to make your own VIs, since all of this code is the same and it's just repeating, you can just use a VI to pretty much have all this code inside of it, and you just use the VI instead of having to have all of this junk everywhere. It just makes it look a little bit nicer. It does the same thing essentially. It is just, let's see here, we want this one. It just makes it a bit easier to read and see what's going on, because right now it's starting to get a little clustered here and it's starting to get a little bit harder to see what's going on. So if you make your dead zone process just a VI, it becomes a bit simpler and easier to look at. Another thing I suggest is having all of your values just run off of the same double for how much the dead zone is. That way if you want to change it, you just change one and it changes all of them. Alright. So now that we have our dead zones, we are going to determine how we want our arcade drive to work. So what we're going to do for this explanation is we're going to decide that we're going to set a limit on what our values can be to determine our states of our driving. So like I said, we have forwards, backwards, and turn left and turn right. So what we're going to do is say this is our joystick axis. You got the x-axis and y-axis. So let's say that if the y-axis is not past a certain point on the or if the y value is not past a certain point on the y-axis, then we're in turning mode. But if it is past, we're in driving mode, so we're driving forwards and backwards. So what we're going to do is we're going to do something similar to dead zone. We're going to use a comparison, and we're going to use an absolute value, like I said, just to make it easier to deal with the positives, negatives. Don't have to deal with those, make it easy. Alright. So let's say if the absolute value is less than, let's say our dead zone is 0.1, let's just make this 0.25, so that's a quarter. So you need to go a quarter of the way up your joystick in order for it to actually determine what state it's in. And this is going to be just being applied to the left Y. So we take our left Y output, get that, and boom, we have our comparison. So now that we have our bit of code that's determining what state we're in, we need our structure, our case structure, our if statement. We're saying if we're in this mode, do this, if we're in that mode, do that. Okay. So if it is less than, if it is less than, that means we're in the turning mode. So we are going to take our x value, which we haven't used before, our left x value, and this is going to determine how fast we're spinning and also in what direction. And this is going to change a little bit depending on, like, you might need to multiply one side by negative one, the other side by nothing. Really, you just got to write the code and then see if it works, and then adjust it a little bit just to make sure everything goes the right way. Because sometimes forwards is backwards and left is right, and you just got to get that sorted out. All right. So we're going to take our left X input, and now we got to decide, are we turning right or are we turning left? So are we rotating, let's just say that turning right is rotating clockwise and turning left is rotating counterclockwise if you're looking at the robot from above. So let's do a greater than 0. So if our input is greater than 0, we're going to get the case structure for if. So if the input is greater than 0, you want your left side to be driving faster, your left side to be driving the positive direction, and let's say positive is forwards, and your right side to be driving the negative direction, which is backwards. And like I said, this might get a little bit of tweaking in order to get to go the right direction, because it might be that it's reversed, and you just got to get that correct. If it is greater than 0, well, your left side going positive, so I'll take that, bring that as the output. Don't worry about the white squares right now, that just means it's not quite complete. And then let's get let's see, where is it? Negate. And you'll get the negative of your input and give it to the right motor. Alright, now in the other case, you do the opposite. So the right side gets the positive, the left side gets the negative. Okay, so that's your turning done. And now what you need to do is you need to figure out if you're going straight. So if when you're going straight, you'll do a similar comparison where you see if it's your Y input is greater than 0. Remember, go from before the absolute values so you don't accidentally get the absolute value of your Y input, not just a Y input. And now you're going to do another case structure. Link it. And let's say, let's try something else for this side. Instead of doing a case structure, we're going to do a selector. So on this side, we're going to say if it's greater than 0 and it's true, let's just have 2 of them. Let's see where this goes. So if it's the y-axis is greater than 0, they both get the positive value. Yeah, we'll need 1. You know what? I think in this one, you don't need any comparisons. Let's try that. Just kind of think it through. Okay, so let's say in this state, we know that we're above our values that we need to be in order to be in the drive mode, or drive straight. And so we are just going to give them the values. Yeah, this will work because the motors are just having the same output. And the reason we need a case structure here, or we could do a selector if you wanted to, is because our values are going to be opposite, and whichever one, the one that's opposite is changing, and so we want to have that case structure here so that we can change which one is getting the opposite value. Alright, that took too much more brain power than it should have. Alright, now we have our 2 different types of driving complete. I'm sorry if it's not quite perfect for your use case. It's not going to be just quite plug and play. It's going to take a little bit of massaging to get it working. Right, that's our K drive. So now that we've gone through a basic arcade drive, one pretty simple upgrade you can do for any drive mode is just having a half speed button. So we're going to grab one more index array, and then we're going to go to the buttons array, and we're going to go back to our Xbox helper and figure out what button we want. So let's just do left. If we press down left joystick, we're going to go at half speed. And in this case, let's just use some selectors, get a little bit of variety in here. Selectors do look a bit nicer, just because. Let's see. Oops. Just because it take up less space than a case structure. So we got our false, where if it's not pressed down, we just do a normal speed. And then if it is, we're gonna need to divide, create a constant 2. Just kind of paste that at the bottom here and fill it all out. And you connect these two. So now what we have is, if our joystick is pushed down, it will divide both values by 2 and apply them to the motors. And if it's not, then you get the normal values. And you can see that on the constructor here. If you need any help here, can't figure out what it does, just press on it and press Control H, and it will show your help tab on the corner up here, and you can press Detailed Help if you need a more in-depth explanation of how it works, of how that VI works. Alright, let's get rid of all this. Control U, organize everything a little bit, and save that. Alright, one more easy upgrade, or really this one's a bit more complex, for any drive mode is going to be PID Control. What PID Control will allow you to do is it will allow you to, is that not connected? No, it just looks weird. Alright, so what PID Control will allow you to do is it will allow you to accurately control either like the position or the velocity of a motor. And for driving, you're going to want to control the velocity. So instead of doing your basic set output here, which does just percent drive, so it's either 0 to 100% drive or 0 to negative 100% drive, you're going to do a set advanced output. You're also going to get a set PID constants. You want your set PID constants to be in begin after you figure out what they are. So you're going to use teleop to tune it, or PID tuning, in order to figure out what values need to be. And I would suggest you watch a couple videos, YouTube videos, on what PID control is, and kind of figure out and start learning how to tune it, how it kind of works, and just kind of get a better idea of what it does and whatnot. So let's see here. Let's use the same. Let's create a constant. Actually, let's not do that. What we're going to do now is create a control. And this creates a front panel indicator. This is your front panel of your different variables. And this, by creating a control, you can actually edit these while running the program on the robot. So you can edit these live in order to get the tune correct. So let's use that for both of them. Since they're similar motors and doing the same thing, we can just use the same little bit of code there in order to get that to work. Alright. So PIDF slot, that just allows you to have multiple versions of your PID constants if you're doing different tasks. I never really used multiple PIDF slots for a motor. I just used one and tuned it correctly, or got a pretty decent tune on it, and that just works most of the time. Alright, we'll get our set point. Our set point is going to be a bit different because in the last time, or the previous mode, it was just 0 to 100, and that was really controlled by your negative 1 to 1 value. You don't need to have negative 100 to 100. It was just negative 1 to 1. But for velocity control, you use a different type of set point. So for velocity, for the Spark Max, okay, so speed is rotations per minute, and then positions, rotations, respectively. So what you're going to do is you're going to want to multiply. Oh, that's not it. Multiply your outputs by whatever the correct value for that is. I think for the Spark Max it's 5,600. I could be wrong. This could be something you look up in, like, I probably use this in my code somewhere. You could look in my previous code and find it, or you could look on Begin.vi. What we're going to do for now is we are just going to go to Begin.vi, and we're going to try to look it up. So let's see, PID, let's see, Spark Max, PID velocity. Let's see, this one isn't exactly what we are looking for, but see, this one he's getting about 3,000 RPM. So it looks like we're in the pretty much almost the correct ballpark. You can always overshoot, so I could make it 10,000 and just see how high it goes, because we're going to have an indicator, which is another front panel thing. So this is a control. We also have an indicator that gives you an output, a real-time output. So let's see here. Let's actually get that set up now. So we'll go to feedback, and we're going to do to get sensor velocity. I'm going to do that to both sides. So this will give us how fast our motor is spinning, and we can use that in tandem with the set points to figure out if our set points are too high or if our PID needs more tuning. But once you get a decent PID tune, you can start messing around with your multiplication or multiplier on your inputs, just to see how high it goes if you don't know exactly what it should be. So I made a little control for that as well. So while you're running this, you can start at 5,600 while you're just trying to figure out what your different values are. Then after that, just go ahead and make those default, save them, and actually you're going to want to move them into Begin, because you don't want to always keep setting your PIDF constants in Tellyab. You just want to set them once in Begin and be done with them. Alright. You also want to set your control mode. So go with velocity. As you can see, there's a couple different types. I never really used, or pretty much only used velocity and position. So in order to do PID tuning, you're first going to set your multiplier to about 5,600, just to start with, and then you'll slowly increase your P, then your I, and then your D. A lot of times I have found that just P gain is really all you need in most cases. With most time you do PI control. In some cases you can just P, but really it depends on your case, and it's really case by case, and it can be kind of finicky. Sometimes you need D gain, but really it's just going to take some practice to learn how to do PID tuning, and you just really just got to do it. So one thing that we can kind of focus on now is going a little bit more in depth about what clusters are. So as you can see here, you have a PID, you have your PID constants, and this cluster, it's just this brown, has all of these different components in it, and you can make your own clusters by just doing a bundle, or let's see, you can do a bundle by name, or you could do a normal bundle. and it'll output a cluster. So like I could bundle in this and that, and now I have this new cluster output. And you can mix and match different types of variables in there, unlike what you can do with arrays. Next thing you're going to put in a robot probably is some sensors. So most robots will have motors, and you already know how to do that. Basically, you just take the concept of how you do the drive motors and just apply it to any other motors that you have on the machine. But for sensors, so this is going to be like the NavX IMU, or for like a rev sensor. A lot of times, like for rev, they have the color sensor. CTRE has a can coder library, and you'll just do the same thing. We'll do like an open, you'll do a set, then you can use get and close and the Finish.vi to make sure you don't have any issues with that. And really, you just need to start messing around and kind of looking at how everything works. And your sensors are going to plug into 3 different types of connections. It's either going to be a PWM, analog, or DIO input. And analog is obviously analog input, digital is digital input, and you generally use PWM really. And so, let's see here. An example of that is a photo gate is an analog input, while a, let's see here, what else? While a limit switch is a digital input. So those are just a couple examples, and you can see those in here. It's like you got your switches, and I think for the photo gate, it was an analog. Let's see here. For photo gate, you're going to go into here, and it's an analog input, and you just read the voltage off of the photo gate. And depending on if someone's in front of it, it'll go to a higher voltage or a lower voltage. I forgot how it works, but you'll read the voltage off of it, and that determines the state, or the state determines the voltage. So a lot of time you'll have a compressor on the robot. Compressors are pretty easy. Just go to actuators, compressor, do a compressor open, ref num set, and that's it. That's all you have to do. And then you should just and then after that, of course, you go to the Finish.vi, you do your reference get and close and stop, and it should just start. You can put start VI after that, but that is pretty much all you need for the compressor. It's really easy. Solenoids, you have your open, your set, get close, and you can get and set the status of the solenoid. One finicky thing with solenoids is you want to always set their default state in the Begin.vi, or else they won't be declared, initialized when you go into teleop, and that can mess up some of your buttons. Like if you have a button to open and close an intake, if it's not initialized in Begin, the button may not respond the first time you push it. So you always want to do a set for solenoids in Begin.vi. And just some general tips. You always want to avoid loops in any VI except for periodic tasks and autonomous. And then in pretty much every VI except for autonomous, you also want to avoid a flat sequence. So a flat sequence just forces the code to run frame by frame, and so this is generally used in autonomous to do a step-by-step autonomous, and you'll have different tasks running, and once it completes, it goes to the next frame and so on. And you can do like a loop inside of the frame in order for it to stay on that frame until a certain task is completed. Then it will exit the loop using its exit condition and go to the next one. Yeah. Also avoid global and local variables as much as possible, because it disrupts data flow and can lead to some weird errors. Just because LiveView is really supposed to be like a guess you call it a line language or block language, sorry. And you're supposed to use the lines because that really controls the data flow. But if you really have to create a global VI, you're going to go into your global VI, your global data VI, and select what type you want. So let's see, let's go with control, name it test. Then what you're going to do is you're going to click on the icon up here, Control C, and go into the VI you want to use it in, paste it, and then select test. And now you can change it to read and write, and you can do all that. And then for a local variable, you just go to your front panel, and then you do a similar thing, create it, and you got that. You can also just right click on like for this multiply. Nope, that's not what I wanted. You can also just right click on there and create your controller indicator. And then finally, for a custom VI, Control N. I just press Control N there to make a new one. Do a file save as. You always want to save it. Oh, where's it saved? Okay, this one, I'm not sure where this project is saved, so I'm just gonna save it here. So for our custom VI here, we're going to do our dead zone. Let's see here. We're gonna code a little bit. All right, let's grab this section here. That is our dead zone section. All right, now we're gonna create a control for the input and create an indicator for the output. And I think we got that there. All right. So now we have our what's wrong? Oh. All right. So we'll have dead zone input and output. And now, in order to actually get this information into the VI, we have to click on our grid pattern, or our terminal pattern, and you can change it to different patterns if you need more. And left side is input, remember that, and right side is output. So you just left click in there and select which one. The indicators will have black squares, and controls will have just the color. If you want to get fancy, you can like edit the icon. But one thing you always need to do for a VI that you're going to be using multiple times at once is you need to use pre-allocated clone reinitial execution. That just means that it can have multiple instances of this VI running at the same time. But if you're just doing one instance of this VI running at once, then you can do non-reinitial execution, and that'll do that. So always make sure to do that. And you will Control C on our VI icon, paste it in here, and now we can replace our. Let's see here. Now you can replace all of this code with now we can replace all this code with 4 of our VI. And that's how you make a custom VI.